Hello everyone, I'm Zhenghong. Today I'd like to introduce my research direction about perovskite solar cells. Solar cells are widely used, such as aerospace construction, and so on. At present, solar cells have developed to the third generation, like dye-sensitized solar cell, perovskite solar cell, and organic solar cell. Among them, perovskite solar cells have many advantages, such as easy preparation, strong light absorption, non-cancer diffusion length, and so on. This is the crystal structure of perovskite. The optional ions for the A site include methylamine, formamidine, cesium, rubidium, and the B site is usually lead and tin ions, and the IX site is a halogen anion. The device structure the device structure of perovskite solar cells like this. According to the relative position of the transponder, the structure of perovskite solar cell can be divided into NIP structure and PN structure. At present, the most efficient device structure is NIP structure. The detailed device structure of perovskite solar cells like this, from bottom to top, are ideal electron transport layer, active layer, hole transport layer, electrode, and the working principle of solar cell like this. Net makes the active layer generate electron hole pairs, and the electrons are transported from the electron transport layer to the electrode. The electron transport layer also used as the growth substrate for active layer, so its flatness is very important. Among the various preparation methods of electron transport layer, spin coating commercial tin oxide nanoparticles is the simplest method, so the electron transport layer is usually prepared by spin coating tin oxide nanoparticles. But the tin oxide nanoparticles are easy to agglomerate, so we need to search methods to inhibit the agglomeration of tin oxide nanoparticles. So, so in this work, we introduced our oligomer into the tin oxide dispersion to hinder the agglomeration of tin oxide nanoparticles. So as figure 1 shows, the oligomer modified tin oxide is adopted as the electron transport layer in the NIP structure perovskite solar cells, and we adopted alpha FAPBI3 as the active layer. After the oligomer modified tin oxide, our highest efficiency exceeds 23%, and there is almost no hysteresis. Then we use the balance characterization to verify whether the addition of oligomer effectively inhibited the agglomeration of tin oxide. Figure 2a shows the molecular structure of this oligomer, and we can abbreviate it as PGDA, which contains a lot of oxygen atoms and both ends are double bonds. Dynamic net scattering spectrum in Figure 2b demonstrated that the particle size of PGDA modified tin oxide solution was smaller than that of the pristine tin oxide solution. We also found that the optical transmittance of films prepared with the PGD-modified tin oxide solution increased. Meanwhile, atomic force microscopy images showed that the roughness decreased, which means that the PGD modified tin oxide films process more uniform electron transport layers than the pristine tin oxide. To further understand the chemical interaction between PGDA and tin oxide nanoparticles, we adopted X-ray photoelectron spectroscopy and Fourier transform infrared spectroscopy. It could be clearly seen from the figure 3a that tin peaks of PGDA modified tin oxide shifted. Moreover, compared to the oxygen peak of purine tin oxide, additional carbon-oxygen single bond and carbon-oxygen double bond characteristic peaks of the PGDA-modified tin oxide could be found, confirming that PGDA was present in tin oxide and interacted with tin atoms. In addition, the functional groups on PGDA that caused the chemical interaction between tin oxide and PGDA was further identified by FTIR. PGD contains three characteristic peaks. They are carbon-hydrogen single bond, carbon-oxygen double bond, and carbon-oxygen single bond, respectively. On the other hand, for the PGD-modified tin oxide samples, both characteristic peaks of PGDA and tin oxide were observed, and the peak of carbon-oxygen double bond upwardly shifted, which further proves the chemical interaction between tin oxide and PGDA. Similarly, we also found that PGDA can coordinate with the net in the perovskite to passivate the perovskite. On the other hand, through the UPS and UV-Vis characterization, we found the conduction band minimum of the PGDA-modified tin oxide shifted forward. Through KPFM, we found the surface potential of PGDA-modified tin oxide increases, compared with the Princeton tin oxide, which is consistent with the UPS results. As we know, the band alignment between the electron transport layer and perovskite determines the effectiveness of electron extraction and recombination rate. Then we further explore the growth of perovskite on the surface of PGD-modified tin oxide. According to the scanning electron microscopy images, the perovskite film grown on the PGD-modified tin oxide substrate contained no pinholes and was denser than the film based on the Princeton tin oxide substrate, which is beneficial to the interface, kernel extraction, and environmental stability. From the XRD patterns, the crystallinity of perovskite based on PGDA-modified tin oxide increased compared to the Princeton tin oxide substrate. From the PL and TRPL, after PGDA-modified, electron extraction efficiency enhanced. So as a result, our device efficiency has increased to over 23%, and the external quantum efficiency of the perovskite solar cells based on PGD-modified tin oxide and Princeton tin oxide were presented in Figure 6b. The edge of the spectrum tail was consistent with the reported perovskite using alpha FAPBI3, and this is the maximum power point output. More importantly, the environmental stability and photostability was greatly enhanced. The enhanced stability of perovskite based on PCD-modified tin oxide could be attributed to the enhanced crystallinity of the perovskite and the more optimized buried interface. So the above is a brief introduction to my own research direction. That's all. Thank you.